The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome back to the 2021 Virtual Viscosity Summit. We are going to give everyone just one more minute to sign on and join us for our next presentation, and then we will go ahead and get started. So give us just one more minute to let anyone who's still logging on get set up, and then we will go ahead and get started. Well, good morning, everyone. My name is Eden Reed, and I am the Senior Marketing Associate for RheoSense. For those of you just joining us, I would like to welcome you all to the 2021 Virtual Viscosity Summit. Now, before I introduce our next speaker, I'd like to go through just a few housekeeping items. As you can see on our agenda, just please note the 1-hour break in our agenda today following this presentation for a lunch. And we'd love to connect with you on social media. So go ahead and follow RheoSense on LinkedIn, Facebook, and Twitter to stay up to date with all the latest news and viscosity discoveries and updates. Each of our speakers has left time at the end of their presentation to answer questions. So we encourage you to ask your questions in the chat pane throughout the presentation so that we can get those answered at the end. And finally, a reminder that all our presentations today are being recorded, and the recordings will be sent out to all registrants 1 week after our event concludes. So don't worry if you miss out on anything. There will be a recording sent your way in just about a week. Now, it is my pleasure to introduce our next speaker, SNF Holding Company Principal Polymer Scientist Dr. Carl Aften. Dr. Aften received a PhD in polymer physical chemistry from Texas A&M and has been responsible for product introduction, mainly of high molecular weight, water-soluble polymers. He has been using instruments from RheoSense since 2011. And today he'll be presenting some factors affecting the viscosity of high molecular weight, water-soluble polymers. So now I'll be turning it over to you, Dr. Aften.
Okay. Dun-da-da. Got it working?
It looks like we're on the back end of your presentation versus the slideshow.
Because I've got I got my title slide showing on my screen.
So we can see your title slide. We can just also see the next slide coming up.
Oh, and I don't know how to change that. Do you?
If you want to just exit out of here and then so just hit probably escape.
Oh, okay.
And then down on the bottom right, slide over all the way to that guy, that slideshow view.
Yeah, that's what I thought that's where I was. Is it still looking the same?
It is. I don't know why.
Yeah.
I think it's sharing the side screen. Dr. Aften, do you have 2 monitors currently?
Yes.
Okay. On your GoToWebinar panel on the right is the show screen.
Okay, hold on. Let me escape. Which one?
Do you see the GoToWebinar panel?
Yeah. Let's see.
Expand that, and under sharing, it should say show screen.
I can't get my mouse to grab it. I can't get over there. Yeah, it's locked up now.
Is it frozen?
Yeah, but I got someone who's helping me.
Okay.
Go ahead. Is that better? Hello?
I think we're now somehow seeing both screens.
Is it possible to disconnect your monitor for the time being?
Yeah, I guess so. Like that. Hopefully that'll help.
You may have to stop sharing and resharing.
Are you guys seeing anything?
Can you go to the can you expand?
There we
Yes,
go.
we're good now.
Okay.
Now it's perfect.
Okay, except how do I get a pointer now? Yeah. But it's not connected to my mouse. Okay. Everything there? Okay, thanks. Okay, sorry about all the technical difficulties. What I'm going to be doing is going to be talking about high molecular weight polymers that are water soluble. And when we're talking about things, we're typically talking about, if we're talking about milligrams per mil, we're talking about 0.01 range, so a little bit lower than what we're used to talking about. Okay. So anyways, what we're talking about is the high molecular weight. And I'm going to tell you, these are manufactured by the inverse emulsion process, where basically what you do is you make a hydrocarbon phase, which is a paraffinic solvent. You put a surfactant in it, typically one that's highly soluble in that. And then what you'll do is you'll add a water-soluble monomer and water. You will mix that together and it'll form an emulsion that is water internal. So now what you have is a water internal phase filled with monomers and other additives. Then what you'll do is you'll deoxygenate it, you'll initiate it, and all those little polymer monomer packets will make a high molecular weight polymer that's in a water internal phase. Now, that's a very nice thing. You have to use a surfactant package that'll hold a lot of temperature, because you'll go basically from room temperature to 150 degrees Fahrenheit. You want to make sure the emulsion is stable to that. So now what you've done is you've created an emulsion that is very stable with a water internal phase. Well, that's great, but in order to use the product, you have to make that water internal phase destabilize. And when you do that, you have to add other surfactants, which we call inverting surfactants. So what it is these products are very high molecular weight. And if we talk about molecular weights, we're typically, and we're guessing, 20 million molecular weights. So there's an average of 250 MER units in this system. So a very high molecular weight. And the only way you can really measure this is by viscosity, because if you try to rely on light scattering, you have to rely on diluting it to enough where you know that everything is a random coil. And if you do a lot of analytical techniques, just filtering the sample ruins the rheological history of them. So you have to be careful. You can use these methods and get numbers, same with size exclusion, but they're not really good. So we typically rely on viscosity and just give a random number. One thing, when you're measuring viscosity, that's not very easy to do with these, since they're at such low concentration. You typically have certain variables that you talk about. One is, hey, are these separate random coils, or are they still entangled, or are they in random globules? The other thing is when you're measuring these viscosities, you have to worry about, are you on a dynamic time continuum? How many minutes or hours was it after you mixed it? Then you measured it. And also the mixing history makes huge factors in what's going on. That's why I say filtering these samples is usually not a very good idea, especially for very refined analytical techniques, and that's why the Microvisc works so well. One of the things too is that you make all kinds of assumptions when you're measuring. You know, if you're using a co-ed geometry, you'll typically have bob slip, so you have to compensate. At very low shear rates, you have to run them very, very long time, sometimes a matter of days, to actually get the right number. One of the other things, if it's diluted, you have to make sure you're in the range where you're getting enough signal. This is where the MEMS chips come in really good, but they do suffer from one thing. You have to look at relaxation time, and I'll be going through that soon. Environmental effects, everything when you measure water-soluble polymers or any types of polymers, even if it's a hydrocarbon solution like Classic Sense. Temperature effects, you know, you raise the temperature, the viscosity typically goes down because the polymer coil pulls itself in. pH, since these are polyelectrolytes, the pH means is it going to be anionic, cationic, neutral. What type of brine is it? Is it in a one-to-one brine where you're not really getting that much interaction except for charge effects? Or is it a brine where hardness is involved, where you can actually, if it's a certain carboxylic acid, you can start to cross links and the viscosity will change dramatically. Total dissolved solids, total suspended solids will make differences. Like I say, you can measure this in TDS, you can call it hardness, you can call it ionic strength, what's the redox potential that you're working in. And also what type of measurement device are you using? You could have a very nice controlled stress strain rheometer, but you're still going to suffer from a lot of things in certain realms. You use MEMS chips, they work quite well, but as you know, you have to make sure that your channel diameter is of a certain size so you're in the right range of pressure and shear rate limit. So the next slide is just basically showing what we call, these are called drag reducers, or we call them friction reducers. Typically they're called drag reducers if they're in a hydrocarbon phase. They're called friction reducers if they're in a water phase. This was discovered or elucidated by Dr. Toms back in 1941 doing naval research trying to make torpedoes go better in the water or make attack cruisers or subs go faster. What it does is there's an illustration on the bottom, and we'll say that's a pipe flowing to the right from the left, and you get turbulence in it. Well, turbulence is not a great thing. It's great for mixing, but it's not a great thing when you're trying to move a fluid and you have to waste a lot of power to move it. Because typically we're moving these fluids over a mile or two in 4-inch lines, so you create a lot of pressure in that. What this does is it reduces the amount of horsepower needed to drive a fluid. So that means what you can do is say, oh, if I needed 15,000 horsepower to drive this fluid at 100 barrels a minute in a 4-inch line, now if I had the friction reducer, I only have to use half the power. So that's a lot less diesel expenditure. And if you're rig limited and you want to move things, what you can do is say, hey, I can get a higher flow rate with less power. So that's another way to look at it. One thing that you need to have in good friction reduction is a couple of properties. One of them is being that it needs to solvate well. You got to make sure that the polymer swims in the water. If you're going to have a carboxylic acid polymer that's negative and you're throwing a lot of hardness in, it's going to cross-link, and that's not a very good thing. And if you're using cationic, multivalent type additives, you can cause cross-links. A lot of times cross-linking in a very minor sense isn't so bad. That's minor structuring, but if you get too high, things will tend to fall out of solution. Now, since I said these things are in packets, water internal, you got to be able to break those packets, and that's called inversion process. So you have to make sure that all the polymer that you made gets out to the game, and that's not the most easy thing to do. Also, since they're water and oil, you have to make sure that they're stable on the shelf. So here's an illustration from Gracely from 1980. Basically, this is for a hydrocarbon system with non-ionic polymers. And you'll see, everybody knows we've talked about entanglement concentration and overlap concentration that's given by the asterisk. If you look at the red line, basically that's a standard hydrocarbon system. But now when you start to involve polyelectrolytes in water, you see your semi-dilute entangled state actually moves down quite a bit. That's what makes these so interesting to work with. Now, the thing that affects the polyelectrolyte line, that's going to be unique for every polymer and every brine system. You can have a polymer where you're using different types of monomers, different anionics, different cationics. You can use them at different amounts, so your charge density changes, the insertion rate changes, and also the type of fluid that you're dealing with changes. So this is a typical viscosity curve that I know everybody's proud of, the RheoSense curve. Basically what it shows is that you have at very, very low shear rates, if you can measure those accurately, and good luck, you will get a Newtonian plateau, and therefore, as you increase the shear rate, like let's say right in the middle of the graph, now you're in a power law region. So what we're doing is plotting log, and it's a straight line, so you can build all kinds of relationships like that. And then if you get into high shear realms, supposedly a lot of polymers give a Newtonian plateau, but we see quite often in these friction reduction inducers, they actually start to go up. So that's one of the things that we want to discuss. Now, also, if we have the exact same polymer, but we mixed it in at different RPMs, we can get the graph that you see in front of you. Those are all, don't worry about the labels, those are all the exact same polymer from the exact same lot. And as you can see on the log time scale, it took about 60 days for them to reach equilibrium. So if you're measuring something in 1 to 10 or 100 minutes, you're going to get very different numbers compared to the equilibrium length. Now, of course, we're all taught in physical chemistry that things are done in thermodynamic equilibrium. Well, though it doesn't happen very often in the polymer world, especially in the one that I'm dealing with, where we shoot a polymer in, it has to hydrate fully, do its job in 5 minutes, and then it's all done. So that's something to be careful of. So as you can see, it takes very long time to reach equilibrium. Now if I show it on a regular Cartesian plot, that's what it looks like. And these were reaching good equilibrium in about 100 days. So one of the other things they have to worry about is the effect of time. This polymer was down at 0.12 weight % active, and we see if we measure the viscosity in 6 hours, we get the curve on top, and we're actually seeing a little dilatancy at the higher shear rates. And as we increase time, we actually see the viscosity drops. Now this could be going on for many, many reasons. These are unique for the type of polymer and brine system that you're in. But as I say, you do get a little dilatancy early on in these, and it probably has a lot to do with entanglement effects. Now, things are even so extreme as if you're using a cationic polymer and you're putting it in a system where it hydrolyzes, you'll actually see the viscosity when you first make it down in a few hours will be in a certain range, but then after a few days, it's way, way down. But then after a few months, it actually goes higher than where it was before. That's because hydrolysis is taking place. You're taking a cationic system, making it amphoteric, and then you're making it fully anionic. Anionics repel more, so therefore your viscosity is going to be higher. Then what you have here is your typical shear rate profile. So what we have are the curves, and everything in the legend is in order. So if you look on the right, that's the concentration of polymer and weight %. So as you see, they're falling very nice into a power law region in the realm of 10 to maybe 10,000 or 7,000 reciprocal seconds. So that's just showing that, hey, the system is well characterized in all the measurements that we take. Then what we'll do is we'll take it and we'll run the same concentrations, but we'll age them for a little bit. What you see is that the lines do fall on each other after 1 and 3 days if the concentration is high. Concentration high means 0.48 weight %, so that's pretty low. But at the very low concentrations, you're seeing as time goes on, the viscosity drops. So what's the effect of temperature? We're all told what a temperature affects. This is, I typically do use the Microvisc, which is, the stubby version, I guess we say, but I've been using it for a long time. It doesn't do all the whiz bang things of the other types, the MV Rock, but it works pretty good for what I want to do. But what we're doing in this is we're looking at one polymer. It's at 0.12 weight %. And as you see, at lower temperature, the viscosity is higher. And since you're limited to how much polymer you can send in a syringe. It's about 400 microliters, and as you go up in shear rate, the volume that you need to acquire data goes way up. So what happened in this one is I ran a syringe for each one except for the bottom one at 131. Then what I did was, with the remainder in the syringe, cooled it in place in the environmental chamber that comes with the Microvisc, and you can see the viscosity dropped a little. So temperature is extremely important. So whenever I'm measuring things here, I typically run them at 26.6 degrees C, just so I always have a steady signal so temperature doesn't become a great variable. And depending on the concentration in the brine system, sometimes 0.5 degree differences can make huge problems. Another thing about when you're measuring these is how quickly did you load your syringe? Since I said don't filter these, it'll change the sear history. You load them up in a syringe, we've already changed the sear history. So you have to make sure you know what you have. And so we did a study where we did pulling it up fast, which is like in 1 second, 400 microliters. Medium was like 5 seconds, and slow was like 10 seconds. But then what we can also do is we can what's called a soak time. It's a relax time where you let it sit at temperature for a certain period, and therefore now, even though it's still at the same temperature, the viscosity has changed because relaxation is sign of come in, because you stress that polymer when you pull it in. Also, the big thing about these high molecular weights too, pretty much everybody, I'm not a rheologist, I've never taken any classes, I'm not an engineer, I'm a pure physical polymer chemist. But pretty much when you read most textbooks, it says, well, start at low shear rates and move to high shear rates. And then if you want to, you hear about this thing called hysteresis. That means go from low to high and then from high to low. And that's what the blue curve represents. And what you see is they're not falling on top of each other. So therefore you say that's the hysteresis effect for this polymer being looked at. But one thing that we've done recently is actually started at a very high, well, at 2000 reciprocal seconds, brought it down to 200, and then brought it back up. And you see actually the curves fall on each other quite well. This hysteresis phenomenon for these types of polymers basically disappears as the temperature goes up, because I guess as temperature goes up, relaxation comes on a little bit faster. Here's something else. This is huge. This is for all you people that use controlled stress strain or co-et geometry, is that time acquisition is very big. In the Microvisc, it says, hey, if you're running at low shear rates, you're going to need a lot more acquisition time before I can tell you what the average signal is when I plot it. But at high shear rates, it goes through very quickly, but I need a lot more sample. This is an example looking at a co-et geometry system. If you look at the blue S curve, that is at 1.7 reciprocal seconds. And what you'll see is it starts out at 3 centipoise, but as time goes on, 140 minutes later, you see, oh, I'm at like 34 centimeters. So if I took a measurement at any time that wasn't beyond, that was before equilibrium, that's not so good. But now, since I've established a profile across the gap, now I can increase my shear rate, and you'll see the lines come on faster. At 3.4, it's like 17, and at 5.1, it's like 12. And those are relatively flat with time. So therefore, if you take the time to get your shear history established across the gap, and this is like a gap of, I think, 0.17 centimeter, took a long time. A lot of people call this bob slip, but I just call it lack of time for taking a decent measurement. Okay, so now I'm going to get into the real study. That was all just preemptive graphs. The friction reducers, like I talk about, we studied A, B, C, D, E. The charges are given on the left. And if we say anionic, sometimes it means it could be an acrylate. Sometimes it could be a sulfonate. If they're cationic, we only have one. They could be at different types of esters or amides that are quadded. And then if we go to molecular weight, like I say, it's all a guessing game. Once you get above 1 million, you can have whatever instrument you want, but it's basically giving you millivolts and milliamps, and you interpret it as you want. What I'm saying is high is probably greater than 25 million, 20 million, very high is greater than 25, medium is about 10, medium high is about 15. So those are just kind of random guesses. Now here's results with a Microvisc, because I said the Microvisc doesn't have the problems with gaps so much, though there is some possible shear slip as you improve the size of the gap, and we're looking at that. But this is an example. What we have here is 4 GPT of FRF. And this GPT stands for gallon per thousand, because these are liquid emulsions that we add. And that's just, it's about we'll say about 0.12 weight percent. And on the right in the legend, what you'll see is shear rate. So 51 reciprocal seconds to 1500 reciprocal seconds. And this is the profile that you get with this system. As you see, with the very low shear rates and very low relaxation times, you're getting about 10 centipoise difference. So this is something that you have to take into account. Typically, depending on the polymer concentration and brine system that we're working with, we typically run 60-second relaxation time. So that just shows that even in a MEMS chip, which is very sound and very good and doesn't give you a lot of problems that a lot of other geometries do, you still have to think about relaxation time at very low shear rates. And you got to understand too, very low shear rates in a power law fluid, you're going to have much more displacement on the y-axis because the viscosity is higher. Okay, so this is the experimental study progression that I'd like to discuss. What we have here is we looked at various polymers, the FRA through F, and we looked at them in fresh water. We looked at loading, which is what I just talked about, mixing time. Then we looked at a simple one-to-one salt like KCl. Then we looked at a complex multi-salt system, which we call TDS, which is total dissolved solid, which is a mixture of NaCl and KCl and potassium chloride, magnesium chloride, iron sulfate. So it gives you a constant hardness, because that's completely different than a one-to-one salt, where it's only what you call charge, not cross-linking. And of course, yes, as you know, charge depends on certain rules. If it's +2, you square it. If it's +3, you cube it. So your ionic strength really does change quite a bit, but you have to know that. And then we did a study where we looked at 2 one-to-one salts and saw how they did together in a mixture design. Then we looked at sodium chloride, calcium chloride, and then we did studies in a wearing blender, but boy, where you talk about mix shear rate and mix time, duration, we put that into a power system. So I think all of you are used to looking at contour graphs, since I saw one 3D graph was given. I'll just go through this really simply for the typical legends. On the top, you see what FR was being looked at. 3 minutes means the data was acquired 3 minutes after mixing. Time is on the left axis going from 10 to 40 seconds, and loading of polymer is on the x-axis going from 2 to 8 gallons per thousand. And as we see, as we increase the gallons per thousand, we see the viscosity go up. The contour lines are in centipoise. And yes, this is at 511 reciprocal seconds, because if you say viscosity without giving shear rate, unless you're dealing with the Newtonian fluid, people are going to get confused. But the nice thing about this contour plot is that it has a linear relationship, which means it's very easy to understand, and not the correlation, but what we call the R-squared values were extremely high. The adjusted R-square and the R-squared and predicted R-squareds were all like 0.99. So that's saying, oh yeah, draw a nice picture, and it actually does mean something. Now, this is the exact same thing, but only with an expanded sense. So 0 to 10, we didn't run 0, because that makes things crazy. You got to do special log stuff. But anyways, you can see it's the exact same thing displaced. Okay, and then the viscosity, if you want a 3-dimensional plot, there you go. So now we'll just start to get into the variables. As you already saw, the first graph showed 3 minutes and the lines were slanted. Now the lines are getting more parallel to the y-axis, and everything is working out well. We're going from 6 to 14 centipoise in 5 minutes. In 10 minutes, we go from, well, 5 to 16. So you're seeing at the higher loadings, as you increase your time, you're getting a little bit higher viscosity. Now, if we go and look at 30 and 60 seconds, then we see the exact same phenomenon. It's just that the viscosities are changing a little bit. This means that it's good that we've studied the system quite well and understood them. Now what we're doing is we're going to go into using a one-to-one salt like potassium chloride. And in the potassium chloride, what we have in the sense is, yes, we're still seeing lines sloped, but they're sloped in the other fashion. Instead of going from right to left, they're going from left to right. So that means as you increase your KCl, you're actually decreasing your viscosity slightly, though it's still relatively linear and nice to understand. Now what we have here is we have FRD at 5 minutes and 10 minutes. And as you can see, there's a little bit change in curvature. There's a little bit of lean on the bottom, but on the top it starts to bend out. And as you can see with time, the viscosity increases. Now, if we go to FRD at 30 and 60, we're getting different readings. We're actually seeing a little less curvature, but on the bottom right, we're seeing a little bit more viscosity. And as time went on, the viscosity dropped a little bit. And I know these don't mean like much because these are like 1 second in, well, I mean 1 centipoise interval, but that can make a lot of difference when you're dealing out in the oil field and you're calculating your Reynolds number because the viscosity is in the denominator, and at extremely high shear rates, your viscosity change can make quite a bit of difference. Now here's an extreme case of a system that does not like KCl. This is FRA, and as you can see, if we do not have any KCl, we're getting 16 centipoise. But as soon as we start to increase the KCl, we see a rapid drop in viscosity. So that is what you call a highly sensitive system to a one-to-one salt. If you're using very clean water, you'll get very good viscosity and quite a lot. This is the friction reducer that was used in the old days. Got a lot of results with it, and everybody was very happy. But then fresh water started to disappear, and we had to use reused water or pond water or brine water from the oil well areas, and this FR did not work so well. Now what you'll see is FRD, which is typically a very good FR versus FRB in medium to high brine. What we have on the left side is the total dissolved solids, and this is in thousands. So at the top it's 75,000. So that's 7.5 weight percent. And TDS is a blend, like I said, of 1-to-1 salts, also 2-to-1 salts, and some 3-to-1 and some 3-to-2 salts. Just for everybody's recognition, the amount of multivalent salt was always kept constant. So just because it's at 75,000 doesn't mean there's a lot more high valence salt relative to monovalent salt. So what we're seeing here is FRD is very good. Usually when we get into systems like this, you want to get parallel lines like we did with 456 relative to TDS, because that means that the FR really does not care what type of salt water it's in. Now, if we move to FRB, what we typically see is that it's got higher centipoise on the very lower right side, but approximately the same on the left side. Okay, so now if we go to FRE, which is cationic, I still left FRD as a reference. FRE gives a unique feature. You see these curves that you get higher viscosity at low KCl and at high KCl, and that's because polymers of different types like to start to equilibrate in certain configurations. Like I say from the earlier graphs, you don't even know if these are even close to equilibrium in the sense that we're looking at. So now if we go to FRC, which is a very cheap FR, and FRA, which is a standard FR, you'll see, hey, the profiles look extremely different, and that's something that you have to keep in sight when you're working at them. And in the oil field, what we like to look at is cost per centipoise. So if someone wants a desired centipoise reading, they could maybe get by with FRA. They might have to use more of it, but FRA could be cheaper. So that's one of the things that you have to bring into consideration. So now we go at a little bit longer time, and these are the results that you get. FRB is still getting higher viscosity versus FRD, but a little bit more sensitivity to TDS. Same with FRD and FRE. Same type of shape, still with the FRE. Now with FRC and FRA, you're seeing still not the best, even though 30 minutes has come on. So that's just a good way of studying to look that we talked about. Now what we're going to do is go into something a little bit more challenging. Of course, the more challenging, the more variables you have, the more experiments you have to run, and the harder it is to present data. So a lot of times you have to fix certain variables, and here we have sodium chloride versus potassium chloride. And what you'll see is that you get sort of what we call a saddle point or a hill type rheology system. And if we use calcium chloride and sodium chloride, we get more of a linear system. You'll see with the potassium chloride and the sodium chloride, you get a little bit higher viscosities than the calcium chloride, sodium chloride system. And you see how calcium affects it relative to potassium. So from potassium, you can see it's a little bit more sensitive, maybe going from 5.7 to 4.6 centipoise if you don't have any NaCl. And if you do have NaCl, it goes maybe from 5.7 to 5.4 centipoise. So that means KCl is affecting the system more, even though on a molar basis, you have less charge available because the molecular weight of potassium chloride is a little bit higher than sodium chloride. Next slide shows the same thing, but 30 minutes later, and what you're still seeing a saddle phenomenon on the simple one-to-one system, but you're also seeing a linear phenomenon still on the calcium-sodium system, but you've noticed the values have changed. Actually, the viscosities have gone up a little bit, and especially for the calcium system, they've gone up quite a bit. They've actually doubled, which is very interesting because a lot of times with certain other types of polymers, as soon as you start adding calcium, it goes down. Now we're going to get into a very complex system, which was quite a few runs, and I have to fix one variable to show them. And the variable that I'm going to fix is shear rate. So we have shear rate at 200 and 511. Now what this was is we took 5 gallons per thousand of FRB and we put it into a wearing blender, about 1 liter, and then we turned on the wearing blender and we ran it from 1500 to 15,000 RPM, so pretty high. And then what we did is we mixed it from maybe 1 to 9 minutes. So there you're getting your energy input. You're getting shear and you're getting duration. So you're getting shear and power put in. And at 200 reciprocal seconds, you see, hey, I'm still getting a nice linear relationship. That's very nice to see. It's a power law fluid, and I expect maybe something like this. Especially when we go to 511, it's still in the power law realm because we're getting good linearity and the viscosities are lower as you would expect. So what's saying is these polymers, you can really shear them up and they tend to survive. Now, if we look at the same experiments, but at 2,000 reciprocal seconds and 5,000 reciprocal seconds, we're actually starting to see a flattening as the duration goes up. This means that maybe what you've done is you've put it into the system where you're on the far end of the rheology curve where your Newtonian plateaus are supposed to occur. And you're seeing that. So what it's saying that, hey, in these systems, if I go beyond 5 minutes, at least the rheology that I pick up in the polymer does not change so much. So that's refreshing to see. Now, if I want to take those and make them a little bit more simple by fixing 2 variables, I'll present the next 3 graphs. So these are the exact same graphs, just in a different form than the previous contour plots. So we fixed the RPM at 6,500 and ran it for 4.5 minutes. And as you can see, at 2 gallons per thousand, the viscosity is lower. You raise it to 3.5 gallons per thousand, the viscosity goes up. And if you raise it to raise it to 5, it still goes up. They're relatively parallel, and you know, all you power law freaks out there love moving the N prime around in Ks. So these show all the things that you want to see typically in power law fluids. Now, if we just look at the variables of mixing time, what we've done is we've fixed the loading and the RPM. We see, hey, at 2 minutes, I have a higher viscosity. If I go to 4.5, the viscosity drops a little. And if I go to 7, it drops a little bit more, but not in the high shear range. And then if we want to go to this one, we say, okay, look at the viscosity at 3.5 GPT, 4.5 minutes of mixing at various RPMs. So we see as the RPMs increase, the viscosity decreases. So this is just saying that, hey, this system was looked at quite well using, I think, 4 different variables, and everything was nice and consistent. So it says this polymers, even though they're in such low concentration and low viscosity, they're very consistent when you want to study them in a scientific route. So as far as the conclusions go, the viscosity of the high molecular weight water-soluble friction reducer, it's a moving target. So a lot of times customers will come to us and they'll say, I want it to have 15 centipoise. And you go, okay, well, at what shear rate? And they go, I don't know. Then we figure out what shear rate they want. And then they might say, oh, I really want to know it at 0.1 reciprocal seconds. Well, it's very hard to get those numbers. And what you do typically is a power law extraction on those. And as you see, extracting at low concentrations is going to be very difficult. So it's a moving target. You can get whatever viscosity you want. So you just have to make sure that you're very consistent in the way that you do it. What analytical technique, what hydration system are you using, what aqueous environment are you looking at? Now, the thing about this that we didn't explore so much, but like I said, these are water and oil internal polymer packets, and you have to make sure the polymer releases. That's a lot of times very hard to tell by viscosity. It's very easy to tell visually, because if the polymer doesn't release enough, the surfactant package will look in a very special way. And if it releases too fast, that's also a bad thing, because you can have what's called fish eyes. Because a lot of times what will happen is the polymer will come out so fast that it'll cause a very highly viscous layer, which ends up being a protective layer for the polymer in the middle, and the system won't hydrate properly. So a lot of times when you have very low viscosity, it's due to the fact that not enough polymer came out, or it came out too rapidly. So just want to say experimental design works really good. And everything is important. The aqueous environment is extremely important. Time is extremely important. You want to make sure that you use a very consistent, detailed method to gather the data. So you might find that you have to write different procedures for different polymers and different brines all the time. And like we're all talking about, equilibrium viscosity, that's the classical thermodynamic sense, and these typically are more of a kinetic world. So what you're trying to do is figure out what's really going on when it's being used. And that's it.
Well, I just want to say thank you so much, Dr. Aften, for teaching us all about the world of polymers. And we are actually getting some questions in. And so I'll go ahead and start sending these your way, and want to just encourage anyone else who has questions for Dr. Aften to drop them in. But our first question is just, is cost per centipoise the most important factor? And are there polymers that are more effective but have a higher cost per centipoise?
Yeah, cost per centipoise is effective if the selling body that you're going to does not look at cost per gallon price. So cost per centipoise, certain companies do look at that and certain companies don't. And yes, there are certain polymers that are more expensive but will give you higher viscosities at lower concentration. So one of the things is you might go and say, well, I'm selling this polymer for $1 a gallon, but in order to get the viscosity you need, you're going to have to use 3 gallons. Or I'm selling this polymer for $2 a gallon, but you only need a gallon to have it work. So that does happen quite often. Yep.
Important factors. And then what shear rate is most applicable to your application?
What shear rate is most applicable? It depends on, okay, we test these things in friction loops. And in friction loops, the shear rates are typically like 7,000 reciprocal seconds. But if you go into the real field and you're pumping 100 barrels a minute through a 4-inch line, you're going to be probably at about 2,000 reciprocal seconds. So one of the big things is always a problem is what we call the scaling factor, which is, hey, I run all my experiments on a flow loop, which takes 5 gallons. And I can't generate the Reynolds numbers that you guys generate in the field. I might be lucky to generate 170,000. But then there's this thing called the Moody chart that once you move out, your friction factor with Reynolds number doesn't change too much. So in the field, they're constantly running million Reynolds number, but their shear rates are only 1,500. So a lot of people have done scaling laws based on shear rate and Reynolds number and found them not to be highly effective or transferable. Some people have had better luck with matching flow velocities. And the thing about these flow velocities, of course, since they're non-Newtonian, they're more blunted profiles than your standard parabolic profile. So if you're even trying to use Moody arguments on a friction reducer, that makes it kind of difficult. But that's what we're stuck with. Typically, when we deal with non-Newtonian fluids, we go into what's called a generalized Reynolds number approach, and that seems to work a little bit better. It gives you much higher shear rates. And of course, the wonderful thing about the MEMS technology is it uses the Weisenberg-Rabinowitz correction. So a lot of times when you get a viscosity number in front of your face and a shear rate in front of your face, you have to replug it into a certain equation to make sure, oh, now my actual shear rate is this and my actual viscosity is that. So that's something you always have to be aware of. Yeah, Rabinowitz, it's Weisenberg, Rabinowitz, Moody, I think. Yeah. Okay.
We're definitely familiar with that internally. And then next question is, have you characterized the polymer using dynamic oscillatory tests to measure complex viscosity?
We do put these on controlled stress strain. Some people believe in that quite a bit. I typically have a hard time doing that. You know, we do use complex viscosity, and we look, you know, it's very trendy right now to look for what they call crossover points. But in the realm of dilute polymer that we're working with, you typically don't get crossover points. So, but hey man, if you've got a controlled stress strain rheometer and you have analysts that know how to use them and not break them, you're way ahead. I mean, the one thing that I really like is I can go get a controlled stress strain rheometer for $70,000 and fix it with a double gap geometry so I can study dilute polymers. Or I can buy a Microvisc for $6,000 and do the things. Now, one thing, the Microvisc is much slower in acquiring data. I have a rheologist. I said, hey, can you run this on controlled stress strain? And he's got so many experiments done in a couple hours where I'm sitting here for like a day.
It definitely is not as quick to run the test, that's right, as even as our other instruments as well, but it is great for portability, I think.
It's great for portability. It's what we call pickup truck worthy. We typically use something called a fan 35, which is pickup truck worthy. That Microvisc is very handy. And like I say, the time to acquire data, if you're in the high shear rate range, it doesn't take very long. If you're in the low shear rate range, it takes sometimes, I think the longest it's taken me is, I think, 68 minutes to acquire one data point at, I think, 5 or 6.8 reciprocal seconds. And typically the thing is we're dealing with MEMS chips, deal with RheoSense. I've always been guessing at it, but they've been very good at helping me out. I typically use a 50 micron channel for my very dilute systems. So I can study very low viscosity, low shear rates, but recently I've moved up into about 40,000 reciprocal seconds or 48,000 reciprocal seconds and been quite happy.
We love to hear that. Did anyone else have any questions for Dr. Aften they wanted to drop in the chat before we take our short pause for an hour for a lunch break? Well, as I've said in our last presentations, if you did want to connect with Dr. Aften or have questions that maybe come up as you're rewatching the recording of this presentation, please always feel free to send those questions our way. And again, we are happy to be kind of a middle connector between yourself and Dr. Aften, or connect you directly so we can make sure to get those questions answered. And then I just want to remind everyone before we wrap up this presentation, we do have 2 presentations this afternoon after our lunch break. We will have Shumshir Mohammed, who's with Kraft Heinz, and then our own RheoSense research and development team will be presenting at 2 p.m. Pacific time today. So Dr. Aften, I would just like to thank you again for taking the time to present with us today and to share your expertise and wisdom with us. It was a great presentation and we really appreciate it.
Yeah, thanks a lot, and thanks for bearing with the technical difficulties in the very beginning.
Oh, of course, we all have them. It's a part of this change we're adapting to as we take a lot of these meetings virtually, and I'm glad we got it sorted out and we're able to get through it without any hitches.
Thank you.
Well, wonderful. And so everyone, go ahead and enjoy the next hour, and we'll be back on here for our next presentation at 1 p.m. We'll be on at about 12:55. Everyone should get an email 1 hour in advance of the link directly to the next presentation to prevent any confusion. But if you don't see that link coming through by about 12:15, please go ahead and ping us, m@rheosense.com, and we are happy to shoot you that personal link as well to make sure you can get on. And if you have any questions in the next hour, we are available to answer those as well. So everyone have a great lunch break, and we will resume here in just about an hour.